Hello everyone. Today we will study about the working of p-n junction diode. In the past lectures we have studied what is diode, then how the diode is constructed from a semiconductor material and how the depletion layer is formed. So, today we are going to study how the p-n junction diode works. So, to understand the working we must know about the biasing process. So, the working of the p-n junction diode can be understood through the biasing process. When an external source of energy is applied to a p-n junction, it is called a bias voltage or simply biasing. Now, here we have to understand the word biasing. If a p-n junction diode is kept ideal, or we can say that when no voltage is applied across its anode and cathode, it is called as unbiased diode. But as soon as when an external source of energy or simply a voltage is applied to a diode through its two electrodes, the diode is said to be biased and the voltage is called as bias voltage. So, the term bias refers to the application of DC voltage to set up certain operating conditions. So, the application of DC voltage is called as bias or biasing. This method either increases or decreases the barrier potential of the junction. So, by applying the voltage we can either increase or decrease the barrier potential. As we all know, when the depletion layer is formed, a barrier potential occurs between the two layers or the two regions, that is P and N. So, that potential can be increased or decreased by applying the external voltage. So, on the basis of that we have two types of biasing, that is forward biasing and reverse biasing. So, following are the two bias conditions applied with respect to the p-n junction diode. The first is forward biasing. When an external voltage is added of the same polarity to the barrier potential, which causes an increase in the width of the depletion region, that type of biasing is called as forward biasing. Or we can say that when a particular polarity of voltage is given to the diode which adds same polarity to the barrier potential, it is called as forward biasing. Similarly, reverse biasing, when a p-n junction diode is biased in such a way that the application of external voltage action prevents current carriers from entering the depletion region, it is called as reverse biasing. In simple words, we can say that the type of biasing which allows the current to flow from anode to cathode, it is called as forward biasing, and the type of biasing which blocks the current from flowing from anode to cathode is called as reverse biasing. Now, let us study in detail what is forward biasing. Forward biasing of a diode is a process in which an external voltage is applied across the diode in such a way that it allows current to flow through it. After applying the forward biasing, the depletion layer is removed and the current starts flowing from anode to cathode. So, this type of biasing is called as forward biasing, which allows the current to flow from anode to cathode. So, in this biasing mode, what happens is that the voltage across the diode's terminal is such that the positive terminal of the diode, that is anode, is connected to the positive side of the voltage source, and the negative terminal of the diode, that is cathode, is connected to the negative side of the voltage source. This means that as we know, the anode represents the positive sign and cathode represents the negative sign. So, when the positive terminal of the diode, that is anode, is connected to the positive side of the voltage source, Suppose we are taking a DC source and it is having again two terminals, that is positive and negative. So, when the positive of the voltage source is connected to the positive of the diode, that is anode, and the negative of the voltage source is connected to the negative side of the diode, that is cathode. So, this type of biasing mode is called as forward biasing, and this is the favorable condition to remove the barrier or the depletion layer and to overcome the barrier potential. So, the following figure shows the working of forward biasing. So, in this figure we can see a voltage source is taken in which the positive side of the voltage source is connected to anode, and as we all know, the anode is the electrode which is connected to the P side, and that is why it is representing the positive terminal. Similarly, the cathode is terminal is at the N side, which is representing the negative terminal. So, when the positive terminal of the voltage source is connected to the anode, which is positive, and the negative terminal of the voltage source is connected to cathode, which is a negative terminal, then it is called as forward biasing. Now, what happens here is that the positive current starts flowing through the diode. Below the figure here, the graph is showing the unbiased junction barrier voltage and forward bias junction barrier voltage. Here we can see that the barrier voltage is overcome by using the forward bias voltage. As soon as the voltage is applied in the diode, the electrons present in the P side starts moving towards the anode, and the holes present in the N type starts moving towards the cathode, and similarly the holes starts moving towards the P region, means the depletion region, and the electrons in the N region moves towards the positive charges of the depletion layer. In this way, the majority carriers, that is in the P side, the majority carriers are the holes. The holes moves towards the depletion region, where it gets recombined with the excess electrons or the negative charges, and similarly the excess charge carriers in the N type, which are the electrons, they moves towards the depletion layer where they combines with the positive charges, and in this way the depletion region, or we can say that the barrier potential is overcome by the forward biasing. Now, let us briefly study in detail what happens during the forward biasing. The forward biasing condition reduces the barrier potential at the p-n junction of the diode, making it easier for charge carriers, that is electrons in the N type material and holes in the P type material, to cross the junction. In simple words, we can say that how current can move from one end to another end. Current can only move when the majority carriers crosses one region to another region. So, when the forward biasing condition is applied or the forward voltage is applied, the barrier potential at the p-n junction of the diode gets reduced, making it easier. So, once the recombination process at the barrier region or the depletion region starts, it makes easier for the majority carriers to move from one region to another region. So, here electrons in the N type material moves from N region to P region, and the holes in the P type material moves from P region to N region, and they are allowed, and the condition gets favorable to cross the junction. When the applied voltage is sufficient to overcome this barrier potential, the diode starts conducting current. As we have studied in past, depending upon the material, there are certain amount of barrier potential. As we all know, for silicon and germanium, this voltages vary from 0.7 volt to 0.3 volt depending upon the type of material. So, for a particular material, at least that amount of voltage should be applied to overcome the barrier potential. So, once that voltage is applied which is sufficient to overcome this barrier potential, the diode starts conducting current. It is essential to ensure that the forward current does not exceed the maximum rated forward current specified for the diode, as exceeding this limit could cause the diode to overheat and fail. As we all know, any electronic or electric circuit or any device or any machine, they are having a rated value. That means, this rated value shows that a limit of voltage or current or power which can be applied to that device or component. In the similar way, diode is having a particular limit, or which is set that maximum rated value. So, when we are applying a forward voltage or forward biasing is applied, the amount of voltage should be such that due to that voltage, when the current is flowing, it should not exceed the maximum rated forward current, and so that the diode works under normal operating region and operating condition, and that current should not affect or it should not create any heat, so that the diode get damaged. Now, the key points which arises during the forward biasing of diode. First is the conduction. So, by applying the forward biasing, the conduction process can be done, or it gets started in the diode. So, when the diode is forward biased and the applied voltage exceeds the diode's forward voltage drop, typically which is around 0.6 to 0.7 volts for silicon diodes, the diode becomes conductive. So, once the barrier potential is overcome by applying the external energy external source, the diode starts conducting. That means, it becomes from semiconductor to conductor. It allows the current to flow from anode to cathode. Now, the current starts flowing from the anode to the cathode, allowing the diode to conduct electricity. So, once the current starts flowing from anode to cathode, the diode conducts current and the electricity starts flowing through it. So, in this way the depletion layer is removed and the potential barrier, or we can say that the voltage is overcome, and the diode is change its application, or we can say that mode from semiconductor material to a conducting material. Next key point which arises during the forward biasing condition is the resistance of the diode. So, during the forward biasing condition, the diode offers low resistance. So, in the forward bias mode, the diode offers low resistance to the flow of current, and since the resistance offered is low, so the current easily flows from anode to cathode. Once it starts conducting, the voltage drop across the diode remains relatively constant. There is appreciable amount of voltage drop which arises due to resistance in the diode, but that remains constant during the working. So, appreciable amount of current, or we can say that the rated current can flow from anode to cathode in the forward biased condition. Now, the third key point is about the protection diodes. So, forward biased diodes are commonly used as protection devices. For example, in circuits to protect against reverse voltage or voltage spikes. So, let us understand this in detail. As we know, in many circuits, to protect from reverse voltage or the over voltage condition or voltage spikes, the diodes are used. So, diode blocks the voltage during the a reverse direction, we can say that when the voltage spike appear. So, in the forward bias, diodes are commonly used as protection devices. Next biasing condition is reverse biasing. Reverse biasing of a diode is a condition in which an external voltage is applied across the diode in such a way that it opposes the natural flow of current through the diode. In this biasing mode, the positive terminal of the diode, which is anode, is connected to the negative side of the voltage source, and the negative terminal of the diode, that is cathode, is connected to the positive side of the voltage source. So, in this reverse biasing condition, the positive terminal of the voltage source is connected to the negative terminal of the diode, and negative terminal of the voltage source is connected to the positive terminal of the diode, and that is why this type of biasing is called as reverse biasing. So, this figure shows the reverse biasing condition. So, in this reverse biasing condition, the positive terminal is connected to the negative side and the negative terminal is connected to the positive side of the diode. So, depletion region is increasing during the reverse bias condition. So, in this biasing condition, the working gets reversed, that is the depletion layer gets widened, or we can say that the thickness of the or the width of the depletion layer increases during the reverse bias condition. When a diode is reverse biased, the voltage across its terminal increases the barrier potential at the p-n junction, making it more challenging for charge carriers to cross the junction. In simple words, we can say that when the reverse biasing condition is applied, or the reverse biasing is applied, it makes the charge carriers or we can say that it blocks the charge carriers to move from one region to another region through the junction. It creates or increases the challenge for the charge carriers to cross the junction. As a result, only a small leakage current, which is also called as reverse current, flows through the diode, typically in the nanoampere to microampere range. In ideal case, we can say that no current flows during reverse bias condition, but practically it is not the case. A small leakage current, or which we can say that reverse current flows through the diode, but the unit for that current or the range for that current lies between nanoampere to microampere only. Now, the key points which arises during reverse biasing of the diode is no conduction. Ideally, we can say that under ideal condition, a reverse bias diode does not conduct current, although a small amount of leakage current flows through it. The increased barrier potential prevents the majority carriers, that is electrons in the p type material and holes in the n type material, from crossing the junction. Second point is high resistance. So, as we know, when the current is blocked from moving from one end to another end, that means the resistance during the reverse bias condition is very high. So, in reverse bias mode, the diode behaves like an open circuit and offers very high resistance to the flow of current in the reverse direction. So, during the reverse bias condition, it acts as the diode acts as an open circuit and it offers a very high resistance to the flow of current. Third is breakdown voltage. If the reverse voltage applied exceeds a certain critical value known as the diode's reverse breakdown voltage, also called as peak inverse voltage or PIV, the diode can undergo a phenomena called reverse breakdown or avalanche breakdown. As we have discussed earlier also, for every devices there are certain limit. So, for diode these limits are for the forward direction also and for the backward direction also. So, when we apply a voltage in the reverse direction and when the magnitude of the voltage exceeds a certain critical value, which is called as diode's reverse breakdown voltage, which is also called as peak inverse voltage, in short it is called as PIV, then the diode can undergo a phenomena called avalanche breakdown. In this case, the diode conducts significantly in the reverse direction and a large reverse current flows through it. So, beyond the PIV or peak inverse voltage, the avalanche breakdowns takes place and a large amount of current starts flowing in the reverse direction, and this is called as the breakdown voltage. So, when the reverse bias voltage exceeds the breakdown voltage, avalanche breakdown take place and current starts flowing in the reverse direction. The reverse bias diodes are commonly used in various electronic applications such as rectifier diodes in power supplies, Zener diodes for voltage regulation, and Schottky diodes in some specific circuits. Therefore, we can say that the diodes have applications in reverse bias condition also. As discussed earlier also, there are a lot of applications of diodes. In these applications, the diode works as Zener diode, Schottky diode, and the mode of working is in the reverse bias direction. So, in this manner the diodes can be worked in forward direction as well as in the reverse bias direction. Now, let us study something about the VI characteristics of diode. The VI characteristics of a diode, also known as the current voltage characteristics, describe the relationship between the voltage applied across a diode and the resulting current flowing through it. So, it is a very important characteristics of diode which is plotted between the two parameters, that is the voltage which is applied across the diode and the current which is flowing through the diode. So, the diodes are semiconductor devices that allow current to flow in one direction only and exhibit a non-linear behavior in their VI characteristics. So, the following figure shows the VI characteristics of diode. The characteristics is divided into four, that means the four quadrant, in the four quadrant axis, the characteristics is drawn in first quadrant and third quadrant. So, the characteristics obtained is in the first quadrant and the third quadrant. So, in the x axis we have taken the voltage and in the y axis we have taken the current, which is also called as a forward voltage and forward current. So, let us see in the first quadrant. So, in the forward biasing condition, the diode works in the first quadrant region, where it acts as a closed switch, in which the current moves from anode to cathode. Here one point is shown which is called as knee, or which is called as knee voltage. Knee voltage is nothing but the minimum voltage which should be overcome to allow the current to flow from anode to cathode. That is, the voltage, knee voltage is nothing but the amount of voltage required to overcome the barrier potential, and as we have already discussed, it is 0.3 volt for germanium and 0.7 volt for silicon. Now, moving to the third quadrant, here we can see the diode exhibits a characteristic, a very linear characteristics for some duration, in which a small amount of current flows in the reverse direction, but when the voltage is further increased in the reverse direction, a point arises which is called as reverse breakdown voltage. After that, a breakdown occurs which is called as avalanche breakdown or Zener breakdown. After that breakdown, the current in the reverse direction increases very rapidly, and this shows the reverse direction of the VI characteristics, which is present in the third quadrant. Now, let us discuss in more detail about the VI characteristics. In the forward bias region, when a positive voltage is applied to the anode or P side and a negative voltage to the cathode or N side of the diode, it is said to be forward biased. Initially, at very low forward voltages, the current is negligible as the diode offers high resistance. Now, as the forward voltage increases, the diode begins to conduct and the current increases rapidly. The current voltage relationship is approximately exponential, governed by the Shortley diode equation. This equation we will discuss in the coming lectures. Here just we have to understand the forward biased region, the characteristics obtained is of the exponential nature. The current, when the current starts flowing in the forward direction, it rises exponentially. Now, here the term comes is the threshold voltage. So, what is threshold voltage? In the forward bias region, there is a specific voltage known as the threshold voltage or forward voltage drop, typically around 0.6 to 0.7 volts for silicon diodes. Below this voltage, the diode remains mostly non-conductive, and when this voltage is overcome, or we can say that above this voltage, the diode becomes conductive. Now, second is the reverse bias region, which we have seen in the figure in the third quadrant. When a negative voltage or a reverse bias is applied to the anode with respect to the cathode, the diode blocks the current flow. So, in this region, the diode acts as a open switch and it offers very high resistance to the flow of current. Initially, at very low reverse voltages, there might be some small leakage current, but it is generally negligible. When the amount of voltage in the reverse direction is low, a very small current, which is also called as leakage current, it starts flowing, but its value compared to the actual current is negligible. So, as the reverse voltage increases, the diode enters the breakdown region where a significant amount of reverse current starts to flow, and this can potentially damage the diode if not protected properly. So, we can see from this characteristic in the reverse bias region, the diode should be protected to work beyond the reverse breakdown voltage until and unless it is used for the application in the reverse direction. When the diode is used for the application in the forward direction, it should be protected to block the voltage or current in the reverse direction, and it should not cross the reverse breakdown voltage. If it crosses, a large amount of current will flow through the diode, since the avalanche breakdown takes place, and it can damage the diode by overheating or by increasing the temperature across the junction. Now, the breakdown region beyond a certain reverse voltage known as the breakdown voltage VB, the diode experiences a rapid increase in reverse current. Now, in this region, the diode loses its ability to block the current effectively and can be permanently damaged. So, from this we have seen that when beyond the avalanche breakdown, the current is rapidly increased, and if the protection is not provided in the diode, it can damage the diode. So, until and unless when the diode is designed to work in reverse biased condition, the voltage in the reverse direction is never increased beyond that limit. So, in the VI characteristics we have seen for the forward bias region, the characteristics is obtained in the first quadrant, and in the reverse bias condition the characteristic is obtained in the third quadrant, and the nature of the characteristic is exponential in the forward direction and it remains linear in the reverse direction. So, these are the VI characteristics of diode. Thank you.